Precalc 1.7, Inverse Relations and Functions. So when we are looking at relations versus functions, we know that a function passes our vertical line test and a relation does not. So that means for a function, each input, has one output. And for a relation, it doesn't necessarily have that. So a function is a specific kind of relation. So if we're looking at inverses, one has AB, the other one has BA. We get them by changing our x and y, and we reflect over the line y equals x. So for it to go that extra step and have a relation to be a function, the original function has to pass the vertical line test. And we denote inverses this way. So that's how we'd write the inverse of x. It looks like f to the negative 1 power is what it looks like. So functions pass the vertical line test. We want to add that in. So that means if I have something like this, and I draw a vertical line through it, it crosses only one time. So yes, it's a function. But then if we're predicting about the inverse, we want to know, is the inverse a function? So if I do a horizontal line test, it crosses twice. And so no, the inverse is not a function. Another important thing that we want to add here is that if a function and remember functions pass the vertical line test, has an inverse, and again, inverses pass the horizontal line test. Then it is one-to-one. So one-to-one functions are going to be really important as you do more in math. So that means for each x we have a y, and for each y we have an x. So kind of the definition of a function where each input has one output, forwards and backwards. So a one-to-one function. And those are the kinds of functions we like to work with. So we're going to do a quick sketch of these graphs and predict whether or not the inverse is a function. So the first one I notice is a +4 and it's an x squared, so I know quadratics look like this. And so if I draw a horizontal line, because I want to know about the inverse, if I draw a horizontal line, it crosses twice. And so horizontal line, if it's more than once, our answer is no. So horizontal line crosses twice, which means that no, the inverse is not a function. For the second one, I have x to the 5th power. So this graph could look a lot of different ways, just without using any kind of graphing calculator or trying to graph it. It's a positive and it's x to the 5th. So that means at most 4 turning points, we could have something like this. We could have something like this, 1, 2, 3, 4. We could have something like this. So without really graphing it or coming up with, or doing a graphing calculator or making some kind of table of values, we're not really sure. So if it was like this, we would have to say no. And if it's like this, we would say yes. So these first two do not pass the horizontal line test, but this last one I drew does. And it actually, if we graph this on a graphing calculator, it would look like this last one. Our answer would be yes. But we don't really have enough information with just the equation the way it is right now without using that extra step of a graphing calculator. I would not give you a problem like this on a test where you were given some high-powered function and then expected to be able to tell just by the equation. You would always have a graph to look at. So for finding an inverse, we need to think, is there really an inverse? We replace the f of x with y, we switch our x and y, we solve for y, and then we use our function notation, and then we're always going to state restrictions. So this is kind of review from last year, but we're paying more attention to restrictions this year on the domain. So for 2a, and this one's going to be like a test problem, so I'm going to start it. First, instead of the f of x, I'm going to write y. And then I will swap my x's and y's around. And then I need to go ahead and solve for y. So first thing I notice is that the denominator is a problem. I'm going to multiply both sides by 2y minus 1. And then I'm going to distribute. I can't solve with those parentheses there. And since I'm solving for y's, I'm going to get all the y's on one side. So I am going to, I'm going to just subtract the 2xy. And now I'm going to factor y out. So now I have 1 minus 2x. And then I can divide both sides by 1 minus 2x. And then I kind of noticed something interesting about this function. I know that if I wanted to reverse the order of the subtraction in the denominator, I could factor out a -1. But I forgot to reverse the order, because then if I factor out a -1, my 2x would become positive and my 1 would become negative. And then I could cross those out. So y equals x over 2x minus 1. You might notice something kind of interesting about that. So my function inverse, so f -1 of x, my inverse of the function is x over 2x minus 1. And if I scroll back up to the top, you'll see that that is the function I started out with. So sometimes you will end up with a function that is its own inverse. The other thing I need to do here is worry about restrictions on the domain. And so remember, for restrictions, if I have a fraction, my denominator can't equal 0. So I'm going to write equal to 0 and solve. So that would mean that my x cannot equal 1/2. So they did not ask me to put this in interval notation or anything here, just to give restrictions on the domain. So here's my inverse, but x can't be 1/2. All right, on the second one, I'm going to follow the same steps. First, I'm going to put a y in for f of x. So y equals 2 times the square root of x minus 1. And then I'm going to switch my x and y around. And then we have to work on solving y. So I need to get inside that square root. So I'm going to start out by dividing by 2. And then I will square both sides. So x squared divided by 4 equals y minus 1. And then my last step is going to be adding 1 on both sides. And now we'll rewrite with function notation. So I do need to find if there are any restrictions on my domain. And I know there has to be, because my original function was a square root graph. So it was a graph that looks like this. But my answer right now is a parabola. Oops, I cannot scroll for some reason. My answer is a parabola. So the inverse needs to be the reflection. Like, I can only have half a parabola here. Something's going on. So I need to figure out what I need to do to fix it. So I'm going to go back to the original, and I'm going to find my domain and range for my original. And then I know that the domain and range of my answer is going to be swapped. So my domain is x minus 1 greater than or equal to 0, because the part inside my square root has to be greater than or equal to 0. That means x is greater than or equal to 1. So then my range, if I put a 1 in, 2 times square root of 1 minus 1, 2 times square root of 0, which is just 0, my range would then be y is greater than or equal to 0. So if x is greater than or equal to 1, y is greater than or equal to 0. So when I go down to my new inverse function, we know that an inverse swaps x and y. It swaps our domain and range. So now our domain is going to be x greater than or equal to 0, and our range is going to be y greater than or equal to 1. So they really only ask for restrictions on the domain, so I would just say greater than or equal to 0. But I really like finding both parts of that and kind of showing how it's connected. So for composition of functions, that's when we put one function inside the other. And when we're using composition to show inverses, what we're really doing is we're saying to prove inverses, I must show that f of g of x equals g of f of x equals x. So let's just make sure we understand what that's saying. This is saying if I apply a function and then I apply its inverse, I go back to the original thing I had. And that makes sense. If I start out with a number like 5 and I multiply by something and then I divide by that same thing, I'm going to go back to that original number 5. So inverses cancel each other out. So we should end up with just x. And this is the way that we have to prove inverses. If you prove using any other method, you will not get credit. So to show that these are inverse functions, and this is the kind of problem you'll have on the test, I'm going to ask you to prove it. First, we need to find f of g of x, and then we need to find g of f of x, and they should both equal x. So for f of g of x, that means I need to take this entire function g, and I need to plug it inside here where I see an x. So we'll have 2/3 times that whole function, 3/2 times x minus 2, and then plus 2. So let's see what happens here. When I multiply my fractions, I just get a 1. So right now I have x minus 2 plus 2, and that's just going to equal x. So now let's try g of f of x. So now I am going to take all of my function f. So now I'm going to take this whole function, and I'm going to put it in the second one where the x is. So I have a 3/2 on the outside, and then I'll have these parentheses, and then in the parentheses, I'm going to have 2/3 x plus 2, and then we'll have a minus 2, and I've got to go through and simplify this time. So now I'm working in these parentheses, plus 2 minus 2 would just be 2/3 x, and then 3/2 times 2/3 is going to be 1x by itself, and so I have f of g of x equals g of f of x equals x. So I would say, yes, there are inverses. All right, we have one last math problem. So for our last one, we are going to use a graph of an original function to graph the inverse. So we're going to pretend that we're starting out with, let's just make up a function. Let's say f of x equals the square root of, let's say we have an x plus 1 plus 4. Actually, let's make it x minus 1 plus 4. I want it to match the paper that I'm going to post online. So that would mean that I would start it at 1, 4. It's almost like having a vertex. And if I am graphing an absolute value, I can graph half of a parabola. So I can do a 1, 3, 5, 7. So there's my square root. There's my f of x. So now I want to graph my inverse. So I can either look at reflecting this over that line y equals x. So here's my line y equals x. And some people are really good at just looking at this and reflecting. I know it's supposed to reflect over that. The other method that I could use for this, I thought I could move that f of x over, but it's all attached. The other method that I can use for this, the method that's going to work better for most people, is to list my ordered pairs for f of x. And usually need to do about 3. And then when I am trying to change them over to the inverse, I'm going to switch the x and y. So if my original ordered pair is 1, 4, when I find the inverse, it's going to change to 4, 1. So remember, inverses swap x and y. My next ordered pair is 2, 1, 2, 3, 4, 5, 2, 5. So when I do the inverse, I would have 5, 2. And I think if I do one more, I'll probably have it. My last one is going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So 5, 6 is going to now be 6, 5. So, and I don't really need to worry about what the equation is for that. So now I'm going to try plotting these points. So I have 4, 1, 5, 2, and 6, 5. 3, 4, 5. And so now I just connect, and that's going to give me my inverse graph. So you can tell that they're really clearly reflected over that line y equals x. That is all we have for notes today.